All right, so today we're going to be talking about redox, mostly just kind of general redox. We're not doing any electrolysis, we're not doing voltaic cells. We're just going to stick to some general redox ideas. First off, being redox is reduction and oxidation. That's where it gets the names. Reduction and oxidation. So to talk about this, one of the good things to remember is that reduction is a decrease in oxidation state, and oxidation is an increase in oxidation state. Now, the problem with redox a lot is there's all these terms that are used almost interchangeably, sound the same, sound different. Like I'm already using the term oxidation in describing reduction and oxidation. So what does oxidation in this term mean? Well, decrease in oxidation state basically means that you are gaining electrons, while oxidation means that you are losing electrons. And if you were to look at any given element, such as element X, if element X went from a +1 charge to a -3 charge, it would have gained 4 electrons. That would be a reduction. If element X went from a +1 oxidation state to a 3 plus oxidation state, then in this case it lost 2 electrons. So that is an oxidation. So that is kind of the easiest way to look at reduction and oxidation. It's kind of what's going on with the electrons. So now we have to think about this term oxidation state. So I'm going to go ahead and describe that over here. Oxidation state. The oxidation state is kind of the way that you look at all these values. So it is kind of the charge of an element or atom, ion in a compound or alone. So pretty much the charge of an element, atom, ion, whatever you're talking about, either in a compound or alone. So for example, if we are to look at sodium chloride, a pretty basic example, this is an ionic compound. So in this ionic compound, the overall charge of this is 0, neutral charge. But if we look at our oxidation states, we find that our sodium has an oxidation state of +1, and our chlorine has an oxidation state of -1. And we kind of just know this inherently in an ionic compound like sodium chloride. Sodium is an alkali metal. And alkali metals always have a +1 oxidation state. Meanwhile, chlorine is a halogen. And halogens usually have a -1 oxidation. Oops. Oxidation state. So before we really get into redox, we need to get really good at recognizing oxidation states. So that's what we're going to do first. There's a couple rules that we can usually follow. The rules are generally, one of the major ones is oxygen. In a compound, it almost always has a -2 oxidation state. I'm just going to say OS because I don't want to keep writing that out. -2, 2 minus, whatever you want to do. I'll actually write it correctly. It almost always has a 2 minus oxidation state. There are some exceptions. There are 2 exceptions. Oh, that's a lie. There are 3 exceptions. The first one being with fluorine. With fluorine, oxygen will be positive. And we'll explain that in a moment. The second one is in H2O2, hydrogen peroxide. Oxygen will be 1 minus. And lastly, in elemental oxygen, O2, it will have an oxidation state, it will have an oxidation state of 0. That's a 0, not an O. So oxygen is kind of one of the most basic ones we'll see around, so we want to keep that in mind. The other 2 notable things that we want to talk about are hydrogen. It will pretty much always be a 1 plus oxidation state, with the exception of H2, where again it will be 0. So you'll notice a pattern between that and this. It is that elements alone, they have an oxidation state of 0. So for example, iron, iodine, that goes for diatomics, sodium with no positive, just sodium metal, aluminum metal, I mean, any of these cases, hydrogen, bromine, they all have an oxidation state of 0. So when we're talking about elements alone, it's always going to be 0. So that's a good way to recognize them. So as we do that, we can start looking at compounds. So let's try some examples. Starting off with something really basic like H2O. Well, first off, I noticed that overall, it is neutral, no charge, which is really good because that means we know our charges must balance out. If we think about both our rules, oxygen is going to be 2 minus, hydrogen is going to be 1 plus, but we have 2 hydrogens. Right there, we have the 2. So together we're going to have 2 plus, 2 minus. They balance out to form 0. Our oxidation states of both elements are 0. Cool, we've recognized them. We're going to move on to something a little bit harder. So now let's try SO2, sulfur dioxide. In sulfur dioxide, once again, I notice that the overall charge is 0 because I don't have any charge up here. So we're going to start off with our rules. We're going to look for oxygen. Oxygen is going to be 2 minus. But in this instance, we have 2 oxygens, as I can see right there. So overall, the charge of oxygen is going to implement a 4 minus charge. That means that the charge of oxygen, the 4 minus, plus, I should rewrite this actually. So that means the charge of sulfur plus the 4 minus of oxygen should equal 0. The total thing is 0. Oxygen, the O2 represents the 4 minus. This isn't oxygen as a diatomic element. This is oxygen in the compound of sulfur dioxide, O2. So we need sulfur to balance it out. Sulfur must be a 4 plus because 4 plus plus a 4 minus will get 0. So in this case, sulfur has an oxidation state of 4 plus. Oxygen has an oxidation state of 2 minus, but we remember that there are 2 oxygens. And together, that equals 0. That's our next step up. Finally, let's go to an even harder example. HPO4 2 minus. Really stepping it up here. So in HPO4 2 minus, we have a couple things to note. One, we have an overall charge. The whole thing overall is going to have a 2 minus charge. When I kind of do these equations, I kind of prefer to actually change 2 minus into -2. So I'm kind of looking at it in terms of math instead of chemistry. So I know my charge of my H plus my charge of my P plus my charge of my 4 oxygens is going to equal a -2 charge. So I'm going to think about this. I know that I have a rule for oxygens. Oxygens are going to be -2, 4 times -2. I know I have a rule for hydrogen. Hydrogen's usually going to be +1. But P is where I don't have a rule, and I need to figure out the oxidation for state for that. So in this case, I have +1 plus P plus a -8 equals -2. I have P plus a -7. That is me combining the +1 and the -8. P plus a -7 equals a -2. Doing some math, adding 7 to both sides. P is equal to a +5, or in the chemistry world, a 5 plus oxidation state. OS. So in this case, phosphorus has an oxidation state of 5 plus. So those are kind of the most challenging things you're going to do when determining oxidation states. Now we get to go into actual redox. And as we do, we're going to come to one of the best ways to remember it, oil rig. Oil rig stands for oxidation is loss. Reduction is gain. And of course, we are talking about loss of electrons, gain of electrons. It's kind of confusing because, once again, oxidation is also the increase in oxidation state, while reduction is the decrease in oxidation state. And one of the really challenging things about redox is that you're going to have to get used to using these words a lot, which are almost counter to each other, but really they mean the same thing. Loss of electrons is increase in oxidation state. Gain of electrons is decrease in oxidation state. And so you have to make sure that you're not getting confused with the loss and the gain, the increase, the decrease, electrons or oxidation state that may already be confusing right now. So with these ideas in mind, and again, continuing to look at oxidation and reductions, we're going to look at a chemical reaction that does include redox. So let's go ahead and look at the reaction that we actually did in class for our lab. So we have let me pick a different color. In class, we did the reaction of potassium permanganate, KMnO4, and iron sulfate, specifically iron 2 sulfate. So it was this reaction between these two chemicals. However, in solution, because they dissolve into K plus MnO4 minus and Fe2 plus and SO4 2 minus, we can just automatically cancel out the sulfate and the potassium ions because they don't participate. These are what we call spectator ions. Spectator ions. They don't participate in reduction or oxidation, so we just remove them. So we know that we're going to be reducing and oxidizing these compounds. Anyways, to the equation. We found that the equation for this was 8H plus MnO4 minus plus 5Fe2 plus reacts to form Mn2 plus 5Fe3 plus 4H2O. Now, something to note, because we have our H plus and our H2O, this was in an acidic environment, or acidic solution. Now, we don't really have to worry about those in terms of our oxidation and reduction. Those just help as a conveyance method for electrons and to help this reaction go. So with all that said, we want to look at what's being oxidized and what's being reduced. The first thing we can note is that we're only actually looking at the manganese and the iron. We know we're not looking at the oxygen because oxygen appears in H2O. And furthermore, oxygen's always going to be a 2 minus unless we're dealing with hydrogen peroxide or fluorine. And I don't see any of that here. So therefore, oxygen will not be changing oxidation state. Oxygen will be 2 minus here, and it will be 2 minus here. Furthermore, hydrogen will be 1 plus here and 1 plus here. We know from our rules that it will not be changing oxidation state, so we will not be looking at those things. On the other hand, manganese and iron surely might be. So let's go ahead and look at their oxidation states. In this compound, we know that we must equal 1 minus. So I have Mn plus 4 negative 2's from oxygen will equal -1. Therefore, if this is 8, -8 equals -1, Mn must be a +7. So I know that my original oxidation state for Mn is +7, and I'm just going to write that above. All right, looking over at iron. We have one thing, and we already know the charge. It's going to start out at 2+. We don't have to do any math for that. And using that same principle, we know that Mn goes to 2+, iron goes to 3+. So let's take a look at these individually. And that 3+ comes right there. Mn has the journey from 7+ to 2+. Iron has the journey from 2+ to 3+. So in this, I see that manganese's oxidation state gets lower. It goes from 7 to 2. That means manganese is reduced. Furthermore, iron is oxidized. So we know that manganese has gained electrons. Going from a 7+ to a 2+ means it picked up some more negative charges. It gained those electrons. Iron lost electrons because it gained more positive charge. If you take away the negative, it is now more positive. So I can say for a fact that now looking at the compound as a whole, manganese is reduced and iron, specifically iron is oxidized. And we always talk about these in the forward direction, not the backwards direction. Redox, we're always talking about the forward reaction. All right, for terms to now get more confusing. If manganese is reduced, if manganese is gaining all those electrons, then it is actually what is forcing iron to become oxidized. So not only is manganese reduced, but the compound as a whole, MnO4 minus, is the oxidizing agent. Again, because we're talking about these in the forward reaction, we're not looking at the products for this. We're looking at the reactants. What is doing the oxidation? What is pulling electrons from the thing being oxidized? Well, that's manganese, specifically permanganate. Furthermore, in the exact opposite vein, iron is giving its electrons to manganese. And because iron is giving its electrons to manganese, iron, specifically iron 2 plus, is the reducing agent. It is facilitating the reduction of manganese. So you have to get used to these terms, flip-flopping and almost being interchangeable, but not. It sounds like they all say the same thing, but they are not. They're saying different things, just using the same word. So sadly, redox remains confusing like that. All right. So the last thing we're going to do is we're going to look at these reactions as a whole and figure out how to balance these types of reactions. I knew that we had 8 H pluses. I knew that we had 5 Fe2 pluses. But how do we know that? How do we get this full reaction from just this reaction, MnO4 plus MnO4 and Fe2 plus? Well, we're going to have to talk about half reactions. So I'm going to give us a little divider, and we'll talk about half reactions. All right. In our first example, we will take H2O2. Oh, look at that. That is hydrogen peroxide plus HI. And that is going to react to form H2O plus I2. Now, if we want to balance it right now, we can do some balancing. We'll go like that, and we will go like that, and we can balance it. But this doesn't fully describe the reaction. We don't see whether or not what's being oxidized, what's being reduced. So let's go ahead and do our math. So I'm going to start with iodine. I always know hydrogen's not going to change because it's always going to be +1. And normally, oxygen also isn't going to change, except we now have an oxygen exception, hydrogen peroxide. So oxygen's part of this equation. So let me start off with iodine. I notice that if hydrogen is +1, then iodine must be -1. It's a halogen, it usually is. And then if we look over here on the right side, it is 0 because it's in its elemental state. So we will come back to that in just a moment. In hydrogen peroxide, oxygen will be a -1. That is the exception you have to remember. And then it goes to a -2. So let's take these individually now. Oxygen shows us that it goes from a 1- to a 2-. It is gaining electrons, so it is being reduced. Iodine goes from a 1- to a 0. It is losing electrons, so it is being oxidized. So what we're going to do is we're going to now figure out the oxidation and reduction half reactions. So let's go ahead and first look at our oxidation half reaction. So in our oxidation, we're only going to look at the thing that's being oxidized. So we see that we have 2HI turns into I2. We also must define whether we are in an acidic or basic constraint. So in this constraint, I'm going to say we are in an acidic solution. And I'm going to apply that to both of ours. So I'm going to say acidic for both. So in an acidic solution, we can always add two things. We can add H pluses, because protons are what let us know we're in an acid essentially every time. And we can add H2O, water. Acids are usually a solution with water in some way, shape, or form. So to balance this out, I'm going to need to add to the right side H plus. But not just one H plus, I need to add two H plus. All right, so we've added it and our elements are fully balanced, but we also have to balance charge. That is super crucial. And I have a 2 plus charge on my right side, but I only have a 0 charge on my left side. So I need to neutralize this. So not only do I balance charge, but I do that by adding electrons. And I can add electrons because redox is just the movement of electrons. And so those electrons definitely came from somewhere. And if we have a positive charge on the right side, something had to happen where we somehow got electrons away from those things. So we have to kind of add them right back. So we're going to add 2 electrons to the right side. And now we have 2 plus 2 minus, and our total charge is 0. Our oxidation half reaction is balanced. Moving on to our reduction. So in our reduction half reaction, we're going to take H2O2 and 2H2O. So H2O2 plus, or sorry, H2O2 not plus turns into 2H2O. Now the problem is, once again, this is not balanced. We have 2 oxygens on the right, 2 oxygens on the left, but we have 4 hydrogens while we only have 2 hydrogens. So once again, we're going to go ahead and add 2 hydrogens. And these are H pluses. Because once again, we can add H plus because we're in an acidic solution. And now we'll look at our overall charge. We have a 0 charge here and a 2 plus charge here. We're going to do the same thing. We're going to add 2 electrons. And we balance out our charge of 2 minus plus 2 plus. It's a total charge of 0. So we get our final reaction, this one that we see up here, by combining our oxidation and reduction half reactions. So as we combine them, we'll just notice that we take everything on the left and everything on the right and put them together. But before we do that, we need to make sure that our electrons cancel out. And they will in this case. We have 2 electrons and 2 electrons, so when we balance, the electrons will be fine on both sides. So we can go ahead and combine our total reaction into 2H plus 2HI plus H2O turns into I2 plus 2H plus 2H2O. And then lastly, we have H plus on both sides, so we can actually cancel them out. And we end up with the same reaction we had before, 2HI plus H2O reacts to form I2 plus 2H2O, which is the exact reaction we had before, so we know we did our half reactions correctly. All right. So example 2, we're going to change things up a little bit. For our second one, we're going to take the same equation we had up at the top, but we're actually going to figure it out. How did we get these values? So I'm going to take this, and we're just going to start it over. We are going to find the half reaction. We're going to use the half reactions to find our individual original reaction. So I know from this that we are going to get Fe3 plus. We already know what we're oxidizing and what we're reducing, and Mn2 plus. And we're going to break down the individual half reactions. How do we figure out all the extra things? How do I figure out the coefficients? How do I figure out the H plus and the H2Os? We'll figure that out right now. So let's start with our oxidation reaction. Fe2 plus turns into Fe3 plus. Well, I don't need to add anything. It's already perfectly balanced. The only problem is I have a 2 plus charge here and a 3 plus charge here. So I need to add a -1. So I'll do that by adding 1 electron. And there's our oxidation reaction. Done. Easy peasy. All right, the problem is now when we go to our reduction reaction. We have MnO4, and I realize I should start that closer to the middle. MnO4 minus turns into Mn2 plus. The first thing I realized right off the bat is, well, I have one Mn on each side. I actually need to add 4 H2Os to the right side to balance the oxygens. And then with these 4 H2Os, I'm introducing 8 hydrogens. So I'm going to have to go back over to the left and do 8 hydrogens. And this is based in an acidic solution once again, because I have hydrogen and H2O. And so as I go through and balance, I realize, all right, all my elements are good. Hydrogen 8, manganese 1, oxygen 4, same on both sides. And let's go ahead and evaluate charge. I have 8 plus, I have 1 minus, so that's a total of 7 plus. On the right side, I have 2 plus, and I have, that's it. Oh no, this is so far different. 7 plus and 2 plus are quite off, and I can only add electrons. I can only add electrons, which are negative. So I'm going to actually add the electrons to the right side, and I'm going to do 5 electrons. Because now I have 5 minus, 8 plus, and 1 minus, which is going to change our 7 plus into a 2 plus, and my charges are balanced. Perfect. I have my reduction half reaction. So now that I have these two reactions, I can combine them. The issue with combining them comes now from the fact that my electrons will not balance on either side. I have 1 electron versus 5 electrons. And this kind of comes back to that idea that you learn in math, where when you are balancing variables and you have to make sure that they balance on either side or they can be subtracted, how do we do that? Well, there's a pretty simple way. We'll just multiply the entire top equation by 5. This will then apply to everything inside. So we're going to have 5Fe, 5Fe, and now 5 electrons. And so now I can see that my electrons on the right will balance with my electrons on the left, and I won't have electrons in my final balance equation. Now I can combine these two. I will have 5Fe2 plus on the left from the oxidation, plus 8H plus on the left from the reduction, plus MnO4 minus on the left because of our reduction. Going back to the top, I have 5Fe3 plus on the right because our oxidation reaction, plus Mn2 plus 4H2O. And that is how I get our full balanced equation. That's how you can just pull it out. And to make sure it's fully balanced, we can actually check every single part of it. And that's what we'll do right before we finish this. I have 5 Fe's, 5 Fe's. Iron is balanced. 8 hydrogen, 8 hydrogen. Hydrogen is balanced. 4 oxygens, 4 oxygens. Oxygen's balanced. 1 manganese, 1 manganese. Manganese balanced. The last thing we have to do is check charges. So actually, we're going to go ahead and check our charges. 5 times 2 plus, plus 8 times 1 plus, plus 1 minus. That is a 10 plus charge, an 8 plus charge, and a 1 minus charge for a grand total of 17 plus on the left side. We have 5 times 3 plus, we have a 2 plus, and we have a 0. So that is going to be 15 plus, plus 2 plus, for a grand total of 17 plus. Our total charges on both sides are also equal. We've done it, y'all. That is redox. If you can get all these steps down, you will do absolutely fine on all your redox and oxidation states. Hopefully this helps, and have a good one.